Hello there. Thanks for joining us for the webinar. As Darren said, my name is Alex, and I will be presenting this webinar today. And I hope the technology will work. People can see and hear what's going on. So the topic of the webinar is pipe stress analysis. When should it be performed? And what we will be covering is something that it comes up a lot in design of piping systems. There's a lot of piping systems that are designed, installed, and operated for which pipe stress analysis has never been carried out, maybe as part of the design, and then there's others for which it has been very thoroughly and to a very high degree of accuracy. So the question is, when do we actually need to do it, and when can we get away with sort of standard solutions, etc., without going into the detail of formal pipe stress analysis? And this is what we'll try to answer today. The agenda for today's webinar is we'll talk a little bit first of all about what causes pipe stress, so understand different things, different physical phenomena that will lead to pipe stress and potentially failure of pipes. Then we'll talk a little bit about piping codes. Specifically, we're only focusing on two codes, ASME B31.3 and EN13480-3. So both of those deal with industrial piping, process piping, industrial piping. We will look at the approach in those codes. What do they require in terms of the requirements to the strength of the piping systems, how they categorize the stresses into primary and secondary stresses, and what is the difference in the way they're treated. And we'll look at the code requirements for formal pipe stress analysis. Then we'll look at when do we need to perform pipe stress analysis. So this is really the question that is in the heading of this webinar. So once we cover a bit of the foundations and the code requirements, we'll start talking about what is the engineering thinking and engineering decision that you need to make. And then near the end, we'll also talk about if you decided that you do need to perform formal pipe stress analysis, at what stage in the project should you be doing it, and the pros and cons of doing it early or late. And we'll also at the very end touch on what happens for in-service pipes. So pipes that already have been designed, commissioned, installed, and been in operation for a while. Do you need to do pipe stress analysis for them? And if so, when? So we'll talk about a little bit about that as well. Hopefully that will make sense. Straight away, what is not in scope of today's webinar, just because we're limited on time. So first of all, we're not going to touch on pipelines and buried pipe. A lot of what we'll discuss is probably still relevant, but there's significant difference between the environment and the codes for pipes that go under the ground. We will not specifically touch on dynamic analysis and requirements for such. We will not look at any specific code requirements except for B31.3 and EN, so we're kind of limiting ourselves in that sense. And we will not really discuss in any detail the pressure rating of components and pipes. So that is something that you can do and you should do, but that is not really pipe stress analysis. That's just making sure your components can withstand pressure. Again, we will not talk about different type of materials and how they influence the pipe stress analysis, but if there's something that you want to pick on maybe in the questions, I will try to answer. And again, we'll not look in any detail about support arrangements. We will mention them, but we'll not give any specific advice on how you should lay out your supports, again, just because we're tight on time. So hopefully that will still meet your interest. So straight away, let's talk about what causes stress. So first and most important thing that causes stress in pipes and can lead to them failing is internal pressure on the pipes. That is quite clear. And from a very early history of engineers designing pipes throughout sort of industrial revolution, etc., when they, what they focused on most is how can the pipes withstand the pressure and not fail when they get pressurized. When we look at the internal pressure inside the pipe, there are two stresses that are orthogonal to each other. So the good thing about this means they're independent of each other, and therefore you only need to worry about one or the other. So you can see here a cross section of a pipe. On the one hand, you have the pressure that acts on all of this circumference. The same would be on the other side. And what is the reaction force that is withstanding that force pushing on the inside of the pipe? That is the stress inside the walls of the pipe. So the thin wall of the pipe, this is where the stress is. So it's this area times the stress on it has to balance the pressure on the area of the inside of the pipe. So it's that rectangle here. And this is our hoop stress. And we work it out down here. So the hoop stress equals pressure times the diameter divided by 2 times the thickness. And then if we look at the longitudinal stress, so this is the pressure that acts on the whole internal sort of cross section of the pipe in this direction. If you imagine the circle a bit, in that direction, the longitudinal stress again is the thickness of the wall, but it's all the way around rather than along the pipe. So that's the other one. So again, we can work out the equation for it, and we can see how we can simplify it. And the longitudinal stress, in theory, for this simplification for an infinitely long cylinder, etc., that will equal to pressure times the diameter of the pipe divided by 4 times the wall thickness. So a few things to point out here. As you can see, the stress in the pipe is proportional to the pressure, which you would expect. It's also proportional to the diameter, which maybe is a little bit less obvious, but again, for people used to piping, they would be familiar now that larger pipes, if you're going to put a lot of pressure in them, they will have very thick walls, because as the diameter of the pipe increases, so do the stresses in its walls. And as you can imagine, the thicker your wall, the less stress you will have. So the wall thickness is on the bottom of the equation. That makes sense. That is logical. Then if we look at the other really important thing here to note is that hoop stress is always 2 times higher than the longitudinal stress. So therefore, from the point of view of rating things for pressure, we can pretty much ignore the longitudinal stress. We don't need to worry about calculating it, because we know that it's always going to be 2 times less than the hoop stress. Therefore, this is our driving equation. And this equation feeds into all the piping codes. There will be some variation of it. There will be some allowances for safety factors, for material, for joint coefficients, and so on. But in principle, it is this equation that sort of feeds into it, and that's what drives it. And this is how we calculate the minimal wall thickness for the pipe, or the maximum allowable pressure with a given wall thickness for the pipe. And yeah, in terms of if you're having issues, if you look at it and you cannot, you're saying, well, I've done my calculations and my wall is too thin. Well, the answer is very simple. Get a thicker wall, go for a higher schedule pipe. So that's very straightforward, simple calculation. All you need to know is your pressure, your diameter, and you can go from there, and your wall thickness, and you can work out and prove that your pipe is safe in terms of internal pressure forces. What else do you need to think about? Well, you need to also consider the weight of the pipe. So that could be self-weight, and it could also be other things that go on top of it. So what else do we consider? Well, think about the liquid inside the pipe, how heavy it is. Think about any insulation that goes on the pipe, the weight that adds to it. Additional acceleration. So again, normally we would look at the self-weight, so just the weight of it in gravity. But you may need to think about earthquake. That can have a different direction and different size of acceleration applied to it. Ship motion, similar idea. Potentially during lifting, you will have a different acceleration, and so on, some sort of transportation load. So that needs to be considered. The other things for pipes, especially those that are designed maybe to run with gas or steam, which has a very low density, so very low weight when in operation. If they're going to be hydro tested at site with water, then they'll be heavier. So that needs to be also considered when designing the supports. And also think about things like snow and ice. So potentially, especially if you have cryogenic service, for example, it's a very common fault is that if the insulation is breached, then humidity from the air starts to ice around the pipe, and that can create a big blob which is very heavy, and that will add to the overall load. So that needs to be sort of considered as well. Now, how can you work out what would be the stresses in the pipes due to all this sort of thing, all the loads applied? Well, you can do it quite simply using standard beam theory. Treat a pipe as a hollow cylindrical section. You can easily work out its properties that you need for simple beam theory, like your Rogues theory, etc. There's simple software available, or you can just create an Excel spreadsheet, and that will give you an idea of what is the stress in the pipe, how much sag do you expect between the supports, and so on. So you can, again, this is a straightforward enough thing, can be done using standard checks. And probably does not require formal pipe stress analysis if all you're worried about is pressure and the weight, as we discussed here. Again, if you're having a problem, how do you solve it? Well, you just add more supports. You make sure that your supports are closer together and nothing has, too long spans between the supports, and that will solve the problem in terms of stress in the pipe. Another thing very similar to self-weight, but external forces. So think about things like wind and waves, so potentially the wind acting on the pipe, or the wave slamming, accidental loads, if you have potential of something being dropped, or maybe a forklift truck reversing into it, then that's something could happen. Pressure relief valves, if they are not well supported, they will create a moment acting on your piping. pulsating flow, surge of water hammer, vortex shedding, potentially some other things you can come up with as well. But basically, external forces. Again, you can basically treat it as a simple beam theory. Apply the load between the supports, either as a universally distributed load or point load, or combination of the two, and you can work out. And again, if in doubt, you can always add more supports. Your pipe will be restricted in movement, and therefore, you'll solve the problem. Probably, again, if this is all you worry about, you're not in high risk that you really need to do formal pipe stress analysis, because nothing complicated is going on. Now we get to the third and kind of very important bit of it, is the thermal expansion. And that's the bit that sometimes people don't think about, or when they think, they don't really know how to exactly analyze what's going on. So what goes on here is, you can see on this top picture, is an example of a railway track, which in very hot temperature, the tracks expanded. As they expand, they need to start moving, and basically creates those wave pattern and zigzags in the railway. So that's a known common fault. As you can see, the picture is black and white. Nowadays, you're quite unlikely to see it, because people designing railways are well aware of the phenomena. Same as you go over bridges, you normally can feel the expansion gaps that you drive over for the same reason. The long spans of the bridge, they expand, so they need to go somewhere, and that is allowed for, and so on. When you build houses, you put render on the sides, you put expansion joints on them. So it's a familiar effect we all see. And the same happens to pipes. Now, purely solar gain and high temperature, the ambient high temperature rarely affects it. Although again, if you are maybe somewhere in the desert and its pipes heat up just in the sun to 50, 60 degrees, that's maybe something you have to start thinking about. In UK, purely the weather, I would say, is unlikely to be causing trouble. However, what happens with the pipes when they heat up? When they heat up, they grow, they become a little bit longer. Now, this movement cannot be contained. It's not good enough to say, well, I'll just put a really strong support and I will not let the pipe grow. That's the opposite of what you wanted to do, because the point is, this expansion needs to be accommodated or absorbed, as we say. If you look at the little graphic at the bottom, that sort of illustrates the point quite well, where we have a couple of pipes. Look at the longitudinal direction. This will grow and it will push into this direction. It will create that sort of zigzag in the pipe. This is over exaggerated shape, of course, but it just gives you an idea of how it will push. So the important thing is, this elbow has to be able to move in that direction, and this elbow has to be moving in that direction. Now, what is important here is that this length B, this is the absorbing leg. If this leg is long enough, then the curvature is quite slight, therefore the stress is reasonably low. If this absorbing leg B is very small, basically one elbow goes straight into another, they will be pushed really far, so there will be a lot of strain in between those two connections, or those two elbows, and there'll be a high stress at this point, and the whole system will be quite high stressed. It will start to buckle in other directions, and so on. So that is kind of the important bit, that if we have a pipe that is not restrained at all, it's just lying there on the ground, it can heat up, expand, move, and we will not have any problem. But as soon as we start restraining parts of it, we then have those forces, and those forces become stronger the hotter the pipe gets, and the more it grows, but also the harder we try to constrain it if we don't give it a good outlet for that motion somewhere. If the pipes can deform with little restriction, then there's less stress induced into the pipe. So that's basically what we're trying to do. And solution to this problem is more flexibility, i.e. less supports, or supports which are quite flexible, or at least flexible in a particular direction. Now, again, we're not going to go into precise solutions you can use because we don't have time, but that's something to consider. It's not just lack of supports, it's maybe supports that are clever and can allow you to absorb the motion of the thermal expansion while not over constraining yourself, but while still providing support for others. So that's the difference. For the previous loads we looked at, solution was simple: we put in more supports. For thermal, we're now saying we need to take supports away. Now, if you have problem with both of them, you have a heavy pipe that you're trying to support well and you want it not to vibrate and move. On the other hand, you have a low thermal expansion. This is going to become quite tricky. Standard solutions may not work, and this is really where you start being pushed towards a formal pipe stress analysis, where you can accurately calculate what's going on, play with different layouts, and find a solution that satisfies everything. It might push you to the edge of what's allowable, but it still keeps you within the safe allowable limits. And that's an important one. A little bit about layout and routing. So again, we're not going to go in detail of it, but it's just an example that exemplifies what happens. Very simplistic diagram here, but bear with me. So the two blue spheres, circles, let's say there are two pressure vessels on your site, and you need to connect them, and you think, well, I'll go the direct route, straight line between the two, least amount of pipe, save some materials. That would be a very bad layout, and people who work in piping probably know that, especially if this is, two-dimensionally just going straight. It doesn't have a step up or down, so it doesn't have any zigzags. Because what happens here, even the minimal amount of expansion in this line has nowhere to go. Either this pipe needs to buckle and start moving sideways, which is quite hard because bear in mind, pipes naturally are very strong, which is a good thing in terms of, they don't need that much supporting because they're strong shape, they're circular shape. But that also means they're not easy to buckle. They're not like slender members that will just simply move side to side. Or the other option is they're going to be pushing on the nozzles where they connect to the pressure vessels. And that's probably the most likely. If you had something like that, even with quite a minimal amount of thermal growth, you probably would be putting excessive loads on your nozzles and even deforming them or even failing them completely. So that would be quite dangerous. What sort of solutions do you have? Well, you can put an expansion loop like this. So that gives a zigzag into the layout. Now what can happen is this elbow can slide inwards, this one can slide inwards, and those elbows are pushed outwards. And those legs here, the absorbing legs, they allow for that motion to happen like a little harmonica, like a spring. There still will be loads, but they'll be quite low, and you can direct those loads with cleverly putting your supports. What would be a mistake is to put a massive anchor on those corners, which I don't think anyone would do, but if you were, because then you're defying the whole idea of what we're trying to achieve here. But if you have anchors around here that allow the pipe to slide upwards and forwards, then that whole thing will work quite well. Another example of what you can do, well, you could put an expansion joint here. So something that allows for either the pipes to slide or for pipes to move. So there's different type of expansion joints. Again, we're not going to go in detail. You could do that. But I would say that is your last resort, really. If nothing else can work, then you go for that. Very briefly, why? Well, because expansion joints are complicated bits of equipment. They're expensive. They're prone to failure over time. They require maintenance and so on. So therefore, if you can use a few elbows and a few meters of pipe, that's always much better solution than putting expansion bellows. Another thing you can consider is rather than putting simply expansion loops for themselves, is just route it differently. Orient your pressure vessel nozzles so that they already have some movement. And as I say, those legs here, they will be your absorbing legs, and then you need to be proportional to the amount of expansion in this long beam. And that's something you can work out. Another way you could do it all together is by this nozzle being at the bottom or looking to the bottom of the screen, and then you would zigzag all the way around the screen, and that would give a lot of flexibility to the pipe. So hopefully you're getting the point. If you can imagine pushing on this pipe or pulling on it and it moving nicely and like a spring, then you will have less issues with thermal expansion. If it is already taut like a string on a guitar, then there's not much you can do with it. Just another example to visualize it a little bit. We're on the same issue here. So here's a real life scenario where there was some liquid being supplied from this nozzle here up above over the loop and then feeding into various different bits of equipment. There were no pressure vessels at that point, but there was still equipment with sensitive nozzles attached to them. So the issue here was that although the pipe was only about 80 degrees we're talking about, but they kept failing at those Y joints at the where the pipe joins to the pipe. And the reason is that as the pipe heats up, this long stretch, again, it's not just about temperature, about how long your run is. You can always look at the system and say, this is my longest run. This is where my biggest problems will be because it will expand by most and then something needs to accommodate it. And the problem is, as you can see, this is again over-exaggerated schematic from the pipe source analysis software. This elbow is being pushed right up and out, and this is pulling on those nozzles, but those nozzles are really anchored into those big cast bits of equipment. Therefore, the pipe goes under a lot of stress and it breaks at its weakest point, obviously. So that's a problem here. There's not a lot you can do with moving supports around because the pipe itself is already restricted by the nozzles. So the solution that was done at this point, we've extended the loop that goes upwards, so it goes up a bit higher than it did before. The pipe then runs the same route as before, goes around, but now it means that this header was above the bits of equipment. We didn't want to move the items of equipment they already installed at site. And then the branches drop down and across. Now what happens, see those legs dropping down? Those legs were in effect the absorbing legs. So they provided absorption to the expansion. Now the same, this straight bit of pipe still expanded the same way. We're still pushing into this corner. However, now there was a lot more flexibility in the system and the loads were within the allowable range, and that resolved the issues. Okay, so looking at the requirements of the piping code. So quickly, the two piping codes that we chosen to talk about in this one is process piping by ASME, American Society of Mechanical Engineers, and it's code for pressure piping B31.3. So this is generally it's for process piping, but as you may be aware, in USA and around the world and in UK in particular, it is very much the go-to code. If you're not sure what code to use, people often default to it because it is very reputable. It's quite easy to use. A lot of people are familiar with it. So that is very well very well respected code to use. And it applies. So the ASME B31.3 doesn't apply only to metallic piping. It also applies to some plastic piping, etc. as well. Then the European sort of equivalent of it would be the EN13480-3. Metallic industrial piping. So in that particular case, it is specifically metallic. There isn't really a direct comparison European code for plastic piping. There are a lot of different codes for plastic piping, but none of them has the same sort of clout as what ASME would have in that sense. Now, what is very beneficial in terms of this webinar for us, and generally maybe as for us as engineers working to European and American standards, is that when it comes to requirements on the strength of the piping systems and specifically on pipe stress analysis, those two codes are practically identical. There's very, very little difference. I'm not going to focus too much on the differences because I'm trying to give you broad brushstrokes of what the code requires. But generally speaking, the European standard very much bases its approach on the well-proven ASME standard in this case, which sort of helps us. So in a very, without going into detail of which paragraph asks what do those codes require? Well, first of all, both codes start with a minimal pipe wall thickness based on internal pressure. So that is quite straightforward calculation. All you would need is an Excel to do it. That does not require pipe stress analysis. You need to do that. Then your pressure rate fittings need to be pressure rated. So that's any of your bought-in fittings. If you're creating branch connections yourselves out of pipes being joined together, then again, there's rules that you can follow, simple equations that look at the strength, and basically goes back to how strong would the pipe need to be to withstand internal pressure. And that's the main one. So that's all fair and well. And in many applications, that is kind of all you really need to worry to make sure that your pipe is not going to fail in service. Question is, well, what about all those other loads we spoke about? Well, for longitudinal stresses, they need to be kept below the allowable design stress. And I'll show you a formula shortly what it means. But again, it will be down to the point of making sure you have supports that are strong enough and they're closely enough and the spans between them are kept to a reasonable amount. And again, if in doubt, you can either use a rule of thumb sort of thing or your standard supports as per your policy or your specification, or you can go and do a quick calculation between each span, looking at what is the weight, what's the wind loading, and so on. All those can be applied. You still could do it manually if you wanted. You can obviously do it in the pipe stress analysis software, but your answer will not be that far apart from each other. And then after that, it also requires that secondary stresses are kept below the design stress range. Now, what are the secondary stresses? Secondary stresses, and I probably should point out that other stresses we talk about, pressure and longitudinal stresses due to gravity and load, external loads, etc., they are called primary stresses, and they need to be all kept below the allowable design stress, and that is normally about 2/3 yield. Now, for secondary stresses, they need to be kept below the design stress range. And that is basically another value. It's a different value, and it's normally higher than the design stress. And the secondary stresses, they are the thermal ones. Basically, if you have thermal expansion, some other things also fall into that category. But basically, it's where the stress is caused by the fact that the pipe has to deform, and the stress is there by the pipe being held constrained and not allowed to deform. That's a secondary stress. Primary stress is the one where there's a force acting upon it, and it doesn't matter, it can start deforming, but the force will still be there. So the pipe has to withstand the force and basically stop this movement due to force. And this is why primary stresses put more supports, counteract the force, you're done. Or if it's internal pressure, put thicker wall, You can counteract, you can hold that force now from the internal pressure, you sort it, you're fine. Secondary stresses are different. You can't stop them by putting more supports or making a thicker pipe either. It doesn't not going to help. You're just going to have a bigger force acting upon your supports if you put a thicker pipe. So that is the difference. Secondary stresses, they're the ones that are basically caused by the requirement of the pipe to change its geometry. Normally it's thermal growth. Potentially it could be if you have a big anchor that is moved because of maybe say subsidence of the earth, and the anchor has moved. So the pipe needs to also move with the anchor. And once it's moved into that position, it will stay there. And therefore you can almost go to yield or beyond yield because the pipe can plastically deform, but as long as it hasn't broken yet, you haven't reached your ultimate tensile strength, it will just stay in this new position where the anchor has moved to, and therefore it will stay there. So that's why, in general, this is why secondary stresses can go to a higher stress range, which is also defined in the code. So how do you deal with the the longitudinal stresses? Well, very often what people do is they stick with, if they have a well-defined, understood type of loads, and they know what sort of weight their pipe is, and they know that there isn't a law of wind or accidental loads or surge or water ham or anything else like that. It's just simple stuff, self-weight, some wind, etc. Then they use recommended spans, and as long as their spans between supports are kept to that or less, then they feel that they're in pretty safe place. In ASME B31.3, there is no specific tables that give you recommended span lengths, but in its sort of sister code, or its mother code probably, B31.1, which is for power piping, there is, and this is the table out of it. But probably a better one to point you to a more detailed one is Appendix Q in the EN13480 in the European code. This is a small extract out of it, but basically it goes through various different situations that you may come across, different size of pipe, different insulation applied, loads, etc. And you can look at how it is laid out, and then you can compare it to the table, and it will give you for different weight per meter and so on, different maximum length between pipes and so on. So this is easy to follow. Again, it's basically just a matter of following tables and layouts. You don't need to do formal pipe stress analysis. You can work out what the recommended maximum, span between supports is. So this is just a small extract to give you kind of flavor of it. In reality, the appendix is quite big and covers a lot, so covers most eventualities you'll come across. So what do the codes require for longitudinal stresses? This is a simplified equation. That's the one you normally would use, but there is actually a slightly more detailed, which is a bit less conservative as well because it's more detailed. But basically what it says is the longitudinal stresses have to take account of this, and you may recognize this formula. This is our longitudinal stress due to pressure. So not the hoop stress, that's the longitudinal stress. Plus we add to it this. So 0.75 is basically just a factor. I is our stress intensification, which can be found in the codes and appendices as well. Z is the section modulus, so that's the modulus of our pipe. So depending on its size, etc., on the thickness of the wall, that will change. And this is the moments, a sum of moments due to sustained moment. So sustained will be pressure, gravity, anything that's permanently acting upon the pipe over a long period of time. And all of that put together on any section of the pipe has to be less than the allowable stress at the temperature that the pipe is operating at. So it's quite straightforward. Now working out the moments, you say, well, how do I work out the moments? Well, the way you can do it, as I mentioned before, is using standard beam theory. So if you wanted, you could go for each section, model it as a beam, work out the moments, plug them into this equation, and check if this section passes this equation or not. And this one below, it's very similar, but there's one more term, MB. The MB is the moments due to occasional. So this is things like wind or waves or earthquake or something that happens occasionally, does not happen all the time. Similar formula, but basically there will be this factor K added in, which means that you can go a little bit higher on the stress. Again, because occasional, the codes allow you to push a little bit closer to the yield. That's basically what this is about. So that's the B31. A more detailed I'm not going to cover this equation just now, conscious of the time, but just bear in mind that basically that takes account of some of the more minor contributions to the stress. Doing it by hand is quite hard, but that's the equation used in the pipe stress analysis software. So just so you bear in mind, but it's the same sort of idea. And again, very briefly, just to give you a snapshot. So this is out of the European code. Longitudinal stresses, sustained and occasional. It's exactly the same formula. It's written maybe in slightly different terminology, but you will end up with the same result. So again, I'm not going to cover it as it is already there. You'll have it on slides. So basically, both codes have the same formula, which is helpful. Now a little bit about the stress range. So the range is defined by this formula here. SC and SH are the maximum allowable stresses in accordance with the code. SC is at its kind of ambient temperature. It's at 20 degrees when the pipe is cold, and SH is when the pipe is hot. So let's say your system heats up to 100 degrees. That will be stress at 100 degrees for the particular material in accordance with the code. So those you can work out easily, and those you need to work out to do the rest of. Now, what is important to note about this, that we are taking maximum allowable stress, multiplying it by 1.25, and then we're adding another 0.25 to that of another allowable stress. So the stress range as a whole potentially is about 1.5 times the maximum allowable stress. That means that for secondary loads, for loads caused by thermal expansion, we can go about 1.5 times higher than what our allowable stress is for longitudinal stresses. And that may look strange, and you may say, well, how is that? Why is that happening? But that is the point, is because for those stresses, you could go all the way to yield. As long as you accommodate the displacement and then stop, it will not in itself break the pipe. It will just change its shape, but it will stay in that position. Now, there's a little bit of theory there about shakedown and ratcheting. I don't have time to go into it, but I just need you to understand that that is there. And if you want to understand better, you can look it up a bit more detail. But just to understand that the requirements for maximal allowable stress for secondary stresses, such as thermal expansion, are different. Therefore, they have to be considered separately. Now, in the EN, again, this is just a snapshot from the code, but basically it's the same idea, 1.25 times the maximum allowable stress at cold plus 0.25 maximum allowable stress at hot temperature. So again, same idea. And then for formula analysis requirements, so basically that's what we kind of covered. What does the code say you need to fulfill? And that's in terms of each section should pass the equation for sustained loads. Each section has to pass the equation for occasional loads. And then each section has to pass the equation for the secondary loads or the thermal expansion load case. That's all good, but then the question is, how do you work out all those stresses? In some cases, you can do it easily using, as we said, just basic equations treated as beams. For secondary loads, that would be very hard to do. And we'll talk about a little bit about simple ways of doing it, but they're not many and you quickly run out. And that's where you push towards using formal pipe stress analysis. So what do the codes say? Well, they say that you do not need to do formal pipe stress analysis in the case of if this piping is duplicating or replacing without significant changes a system operating with a successful service record. So what they're saying is if it's proven by in-service operation, then you don't need to do pipe stress analysis because we know that it must work. If it can be readily judged adequate by comparison with the previously analyzed system. And that generally is a bit of a point that if an engineer can look and say, look, it's absolutely fine, there's nothing going on there, just leave it, it's fine. You can get away, especially if you say, well, there was a similar design, but that was at 200 degrees. Here it's the same pipe, but we're only operating at 100 degrees. So there's less thermal loads. Leave it, there's no change. But that's an engineering judgment, and you need to be careful to consider, has anything else creeped in, maybe stronger winds, or maybe it's in an earthquake area while the other one wasn't. And then there's a C, and that's a bit of a black magic that's in the code. So it says basically it has uniform size, has no more than 2 points of fixation, no intermediate restraints, and falls within the limitations. So what it says is if you can take your pipeline and break it down into sections, and for each section, you have no more than 2 supports acting. So if you have branches coming off, that becomes very tricky to apply. But once you've done it, for each section, you can put this equation in. And this is basically looking at the outside diameter of the pipe, the distance that it needs to absorb, then the distance between anchors, developed length of piping between anchors. So developed length, that means the total length of all the pieces of pipe put together. And the U in this is the anchor distance. That's a straight line as the crow flies between the two anchors. And you take out the difference between those, solve this equation, and if it is less than this constant K1, and this is different depending on the units you're using, if you're using metric or imperial, If you satisfy this equation, the code says you're fine, there's no problem with thermal, just make sure that all your supports are far enough apart, etc., and then you're okay. If you fail that equation, the code basically says you should go and do proper analysis, formal analysis of your system, because otherwise it's hard to work out whether it will or will not have issues with thermal expansion. That is sort of the idea. Now, with this equation, I'm not going to go in any sort of depth on where it comes from, why. It's easy to apply if you want to. It's easy to do a check, and you can use it. It's been around for a long time. It's trusted. It's very conservative. So again, sometimes you may be better off doing pipe stress analysis and not ending up with an overly conservative design. But it's a bit of black magic in terms of how exactly they worked it out, and it's based on some monograms and so on. Now, the interesting thing is, this is out of the EN code, and it's exactly the same equation, and basically European code has completely left it, including all the caveats and all the definitions and all the constants. So again, that magic rule applies to both ASME and European code. Right, so then we go to a point of, okay, so if the code says we need to do pipe stress analysis, what does that mean? Well, as we said, for same or previously proven design, we can just have a review, decide that nothing is worse off, everything is same or better, therefore we can just pass it by inspection. That's option one, that's easy. We can sometimes use monograms and standard solutions. So here's an example, I'll show you another one. This solution where there's a pipe going through, there's a known amount of expansion that needs to be absorbed. It has a certain rules about where you place guide supports and how big this loop has to be. You use this table to look up values, and you can size your loop. This all can be done without use of software and complex analysis, but it only works if you have a straight line with a loop in it and you follow all the bits. So yes, it's great when it works, but in many cases it's not going to be working for you. I'll show you another example of a monogram. Here's a typical one. Again, two tanks connected in between by the line, no other supports present. Basically, this is like a cantilever method. So if you treat this pipe here as a cantilever beam, that gives you your equation. You can almost solve it yourself, to be honest, based on Rock's principle, knowing how much this is going to expand by and how much you will need to absorb. So again, you can use something like that. That's fine. My view is I'm not a huge fan of use of those monograms and those old school methods for analysis where you have thermal expansion. The reason for that is you get too conservative, and it only applies in a small number of cases, and then in others you either not applying it correctly or you have nothing to cover yourself. So then you potentially go into full proper pipe stress analysis using some sort of software. So this is to the question, when do we do formal pipe stress analysis and what are the risk factors? Things we need to think about is the type of service. So how critical it is. If it was to fail, is this going to be a nuisance, or is there going to be an ecological disaster, or are people going to die? So that's a very important question. Of course, the more harsh the service, the more belt and braces approach you should have, and you probably will be driven towards doing pipe stress analysis, even if there's not much else going on. Pipe size and schedule. So size maybe is less important, but the thing with bigger pipes is that they exert more force on nozzles and connected support structures. So for larger pipes, you want to make sure you make those checks, maybe not for the sake of the pipe failing, but for things that are connected to the pipe failing, because a large pipe expanding or moving or catching a lot of wind could break structures and tanks and things around it. Schedule is the same. So again, if you have thicker schedule, it's a bigger rod that's pushing on everything, so it has more strength in it. Thermal loads, very important. So if you have significant thermal loads, or you want to tethering whether it's significant or not, you probably want to do formal pipe stress analysis to satisfy yourself, because it's very hard to judge by just looking at the system that thermal loads will not cause issues. If you have nozzle connections, especially to sensitive nozzles on rotating machinery, cast nozzles on pressure vessels, then you want to do pipe stress analysis probably. Wind, earthquake load. So those can be done by hand sometimes, but often enough it's easier to do using software. If you require model analysis, so you want to check the vibrations and the natural frequencies, again, it's something that is a lot easier to do using formal pipe stress analysis. So that will drive you towards it if you have vibrations. If you have high pressure, possibly I would say, if it's just pressure but nothing else is going in the line, there's no thermal growth, it's well supported, You probably don't need, you just make sure your pipe is thick enough. But again, like the type of service thing, if it's very high pressure, you really don't want it to fail. So it's probably prudent to do pipe stress analysis, but the big drivers are there. Now, that's the important risk factors. What I'll present to you very quickly now is a few very reputable people giving their rules of thumb. Now, please bear in mind, this is rules of thumb. They are not laws. They're not part of some sort of approved code. So only use them as an inspiration and a guidance, but always apply your engineering judgment, right? So this is from Little PN. It's a very good book on pipe stress analysis by this author, and they have a consultancy. But basically what they're saying is system operating that exceeds 150 Fahrenheit, sorry, it's American, and pipe diameter is 4 inches or above, or temperature exceeds 300, analyze smaller lines than 4 inches. So again, it kind of focuses on the larger lines, but as the temperature gets higher, you start checking smaller lines as well. Any pipe above 12 inches in diameter, some say 8 inches diameter, so again, depends on your appetite for risk. Any pipe 2.5 inches and larger connecting to rotating equipment or heat exchangers because of the load on the nozzles. Any pipe 6 inches and larger connected to pressure vessels. Cryogenic piping, but that always will have quite big thermals already. Hazardous chemicals, so again, I say if it's a very high risk, probably even if nothing is specific going on with it that's making you think it may fail, you want to have this analysis in the back pocket. Short hot runs of pipe anchored at both ends. So as we said, if it's a short run, that just there's no much ability to absorb. When professional review of the system shows system lacks flexibility, if the system is complex, low branching, again, it's just very hard to do anything without formal pipe stress analysis. Your rules of thumb don't really apply there when seismic analysis is required. Another experienced consultancy, Samantha Engineering, they give their view. I'm not going to go line by line, but you will have it on the slides that you can download after. But again, it's similar. There's nothing really here that's particularly different. It has a specific thing, all piping above certain pressure, so it's high pressure lines. It says anything that's in category M fluid. So this is very highly toxic stuff. So again, where a risk of a leak is very dangerous, then you want to do checks on it. All pressure relief systems, but again, that is, I would say, that is true for large pressure relief systems on process plant. If you just have a small system, for example, compressed air in a garage, I wouldn't expect that the pressure relief on that, which has to be there, I wouldn't expect that the forces it generates will be too hard to mitigate with just a good solid support next to it. So again, read that with a pinch of salt. And then another very well represented, very well respected consultant, Bert. That's their view. Again, it's very similar to the one before. So basically, where there's temperature and the larger the pipe diameter, the lower the temperature at which they would recommend you should be doing pipe stress analysis. And also, any lines above DN75 connected to rotating equipment, any pipes above DN100 connected to heat exchangers, and anything over 150 connected to tanks. So again, that's kind of the guide. That bear in mind that a lot of times it's not the pipe that's going to fail, it's the nozzles to which they're connected that will be pushed and broken. In terms of load cases that you need to consider, as a basic case, you need to do your sustained load cases, which will include pressure, weight, and external loads if they are sustained. Occasional load cases, again, pressure, weight, external loads, wind, waves, things like that. Operational load case, which will include pressure, weight, external loads, and thermal expansion. Now, I don't have a lot of time to cover, but the operational load case, you do not check against allowable stress because codes don't require that. There's no requirement in code. But the reason you check them is this will give you a accurate calculation of loads acting upon supports and nozzles, and you can then put it into your support analysis or your pressure vessel analysis and check the nozzle can withstand that force. So that gives you a realistic load on supports and nozzles. And then you need to do an expansion load case, and that is basically operational load case minus a sustained load case, which equals thermal only. So that means you're not worried about pressure, weight, external loads, etc. All you're worried is about this movement that needs to be absorbed, and you compare it to the allowable stress range, and you check whether they pass or fail the code check. You separately may need to consider hydro testing, especially for, say, pipes which normally carry light fluids. And you may need to consider alternative sustained and operational. So what the alternative sustained operational is they will look at if you have your sustained load case, but you apply the thermal temperature, the pipe may move, and it may mean that it will rise off its support. So one of the supports that you think is there is no longer touching the pipe, it's not doing anything, and therefore your moments due to self-weight will be higher because you now applied heat to the pipe. So that's what those load cases deal with. Okay, just conscious of the time, we need to be wrapping up. I'll quickly scan through the next few. Importantly, when do we do pipe stress analysis? So unlike, for example, analysis for pressure drop in the system, which can be done at a very early stage because you don't really mind if the pipe goes left or right, if it's 2 bends or 4 bends, that makes quite small difference to the overall outcome. In pipe stress analysis, it's very sensitive to everything, where your bends are, where your support is, how your pipe is laid out, etc. So really, to do pipe stress analysis, you need to have the route fully defined, schedule of the pipe, all the fittings, location of the supports, they need to be defined before you can do pipe stress analysis. That normally means you have to go all the way to completing your 3D model before you can engage pipe stress analysis. By that point, if you found there's an issue you need to reroute, it will be an impact on cost and schedule to you, and that creates a problem. So there's chicken and egg. Do you first analyze the pipes so you run them correctly, or do you route everything and then analyze? So briefly speaking, what I suggest you do on a project, if you decide that you will need to do pipe stress analysis, create a critical line list, identify those that are most at risk of failing pipe stress analysis, and route those pipes first and do analysis on them quickly. Then come back to do the rest. So normally that means largest pipes, pipes that are hottest, connected to pressure vessels, they need to be routed first. Other minor ones that can be easily rerouted, leave them till later. So move this thing into your project plan. Secondly, what you sometimes do is do preliminary pipe route assessment. What that means is that for particularly high risk where we think there's a very high chance it will fail the code requirements, we routed quickly that line, maybe not with all the full detail, maybe not with all the supports, but we check the load cases that most worry us, for example, thermal load cases. And we see if we are roughly in the green or we are well past the allowable and we need to completely rethink our routing of this pipe. So that can often be done early in the project without all the paperwork, just pipe stress engineer talking directly to the designer in the 3D model, working out something that has a very low risk, and then they leave it, and then they will pick it up when they do a formal pipe stress analysis of the whole run, and it will cover off then. So again, you can be very targeted about when you use pipe stress analysis at an early stage in the project. That way you will de-risk it at a minimal cost upfront. And just a brief one on in-service pipe stress analysis. So normally we do it during design phase, but pipes that have been in service for a while, sometimes we need to look if there's a change in the pipework rating, if it has corroded significantly and we want to continue operating it, that will change its behavior. Change in design conditions. So if the temperature is going to be higher, that's where you need to think or something like that. So for example, if you say this pipe has been working for 20 years, no problems, but now you increase the process conditions, so instead of going to 100, it goes to 200 degrees C, completely different loads. You need to reassess it. If you have movement of supports or anchors, so I say sometimes that happens due to subsidence or something like that, that can happen where some anchors have moved, some supports have moved. Now that changes how the pipe will behave. Or of course, if you had a failure, then you would maybe want to do analysis to understand why did it fail, what was wrong in the first place. So that's something you would look at. So apologies, I had to rush a little bit at the end, and we overrun, I think, by 5 minutes, but we still have time for questions. I think there's been quite a few in chat, so we will move on to.
Yeah. Yes.
Darren, do you want to cover the upcoming courses first?
Yeah, we'll do it very quickly. Thank you very much, Alex. Very interesting, and hopefully all our guests found it equally as interesting. Just for a bit of information, there are a number of upcoming courses on this topic, as you can probably see on screen. So design of piping systems in August in London, pipe stress analysis, which is a virtual course in September, and then the same course again, but face-to-face in London. And then finally in November, we have design of piping systems as well in November. And you can see there's a promotional code that you can utilize as well. I would stress going to the website as well for any further information. That's a great resource for details there. And briefly, if you're looking at a number of people that might benefit from the training, we can do more in-company kind of bespoke to your requirements training as well. But that's enough of the promo. We'll talk about some of the questions now, if you are okay with that, Alex. So first question, we'll just go through them as they came in, if that's all right. You may have answered some of these already in the presentation, but so the first question, have you got any experience of using plastic piping, and what codes and standards would you use instead?
Um, so yeah, that's a good question. So the ASME standard does cover plastic piping in principle, but you need to be careful with how you apply it. As I say, the EN code doesn't. There's a number of different codes. I don't have them off the top of my head, but I can try and point in the right direction when we put the slides up. I don't know if there's an opportunity to add a slide to it. We can put into it, but it roughly would be similar. The difference is majority of plastic piping to date in industry is rarely has been used in high thermal conditions. So normally it's quite cool, just because a lot of plastics will soften a lot and potentially completely melt at high temperatures or burn. So a lot of the time you can get away looking at just the loads that are applied to them and spans between the supports, and you not so often need to do pipe stress analysis because there's not much thermal growth. Because once you get to hot surfaces 100 degrees and above, uh, chances are it's metal. So I don't have a lot of experience of actually performing pipe stress analysis on plastic, but it can be done, yes.
I think this might be a follow-up question. What about small bore pipes?
Okay, so small bore pipes, as we kind of covered a little bit at the end,
Yeah.
it's exactly the same. So if you're talking something like 8 millimeter tubing or similar, it would be very unusual to do pipe stress analysis on it. But because of the nature of the tubing, it normally is designed in a quite flexible way. In fact, if you look often when like some instrumentation is attached, the tube is actually coiled around, so that creates a spring naturally, so you can withstand all sorts of forces and fluctuations in pressure and so on. Um, Generally, so if you talk very small, like say tubing like 8 millimeter, 12 millimeter, yeah, you probably can just route it. Just don't put it a straight line. Put a couple of bends and you'll be fine. And it's very light and it can withstand a lot. If you're talking small bore, like 1, 2 inches, which still is to me small bore in an industry, mostly will be seen as quite small pipes. They are slightly lesser risk, but does not mean they could not fail or they could not exert excessive load on a nozzle. So if it is in hot operation or cryogenic or something like that, yes, I would still do pipe stress analysis just the same.
Perfect. Excellent. Gary asks, why would you select EN versus ASME code? Thank you.
Right, good. Very large question, really. I would say it depends what your specification is, where your plant is. So, if you're starting from scratch and there's nothing defined, it's your choice, so to speak. Um, ASME in America, people use ASME. In UK, oil and gas, people will almost always use ASME, with some rare exceptions now coming in. Petrochemical, a bit of the same. ASME code has been around for a long time, and it's very well kind of reputable in certain industries. If you're in an industry that doesn't have a lot of like predefined, maybe it's something new that's emerging, etc., you could consider either there's pros and cons to both codes. I can't go in detail here about why what the pros and cons are. Two codes are quite similar in many ways, but there is a little bit. EN is a bit more analytical, probably. ASME is a little bit easier to apply. The other thing that you really need to consider is where your project will be built and whether it is easy or not to get materials which are qualified to ASME or EN materials. Because although it's possible to mix and match codes and materials, you're creating a road for your own back doing that. So try to stick to one or the other set of codes. The other thing to consider is that if you need to comply with CE marking pressure equipment directive in the EU, then following the EN standard automatically gets you there. If you do it to ASME, you'll have to jump more hoops to get there. On the other hand, if you're trying to comply with regulation in America, then going with ASME will help. In UK, under the new regulation since Brexit, either of those codes will comply with the pressure equipment safety regulation. So it's your choice.
Excellent. Thank you. What additional considerations might there be for composite piping?
So for composite, so that again, it's kind of similar to the plastic one, if I understand correctly what you mean, where you have composites or fiber and resin reinforced. So yeah, first of all, temperature can really handle very hot temperatures. Some modern things can, but not that many. Also, uh, are they more prone to brittle fracture? So sometimes that could be a problem where, again, which could be an issue, and you need to think about concentration in that sense. So that those I would say would be the main ones. Other than that, the same applies. Your loads due to pressure, etc. Just thicker walls, stronger materials. primary stresses, more supports, but when you get to thermal expansion, you need more flexibility. So the same idea applies in whether you need to do it or not. Again, I would say maybe if you're doing something with composite pipes, I probably would be more risk averse because there's just less practice and experience in the industry. So you're not leaning on as much. While when you're using pipes that have been used for 50, 70 years in a very specific application and people never did pipe stress analysis, you kind of know that in this industry, it's okay because you know what you're doing, so to speak. With composite piping, you're a little bit pushing into the new area, and I would be more prone to do pipe stress analysis, maybe just to prove that you know what stresses are going into them.
Excellent. If the cause of pipe movement is external force, i.e. water, hammer or so, are we still supposed to capture it by expansion loop, or do we need to add additional support to restrict the movement?
So say that again?
Yeah, if the cause of pipe movement is external force, such as water, are we still supposed to capture it by expansion loop, or do we need to add additional support to restrict the movement?
Yes, if it's external force, normally it's matter of additional supports and restricting it. That would be your best bet, really, rather than having expansion loops, etc. The expansion loops are very much to deal with this thermal growth and the movement that may be in the pipe. So it makes the pipe more flexible. The problem with something like water hammer, etc., if your pipe is quite flexible, then actually it means that force will move it more violently side to side and potentially higher amount of deflection on it. So you do want to constrain it because that is basically supports are counteracting the forces. That's kind of the seesaw that you're on. With thermal expansion, it's opposite because if you say this pipe is trying to move because it's getting hotter, I'll try to restrain it. Now the two of them are just destroying the pipe. The two of them are working together to increase stresses. So they're not counteracting each other. They're almost like working together to increase stress. So that's the difference. So yeah, something like external force, yeah, more supports will resolve the issue.
Perfect, thank you. We're running slightly out of time, so we'll crack on as quick as we can. So a question here is, when should you look to use pipe software analysis, and when can you just assess by using basic hand calculations?
Well, that hopefully was covered in a presentation. So they say that those last few slides is an example of where you can. So I think I'll skip a bit, but basically say those are some of the recommendations. Now say there are rules of thumb, but they drive you in a particular direction. So yeah.
Good. We'll give a couple more in if we can. Could you give some comments about DMV RP D101 approach to pipe stress analysis?
Right. So very briefly, that approach itself, it's not a separate code, but it's a very good code to be used, especially if you're working offshore or generally oil and gas or anything of similar kind of size and type of temperatures and pipes. It's a very good recommended practice. I also recommend people are familiar with it. It's not very big. It's easy to follow. It's easy to read, and it gives a good approach to using. Now, it's still you actually will have to still comply with the code. I think it specifically calls out ASME B31.3, but you could use a different code and still follow that practice. It's more about how you go about laying out your approach to the piping.
Okay. Another one then quickly. This is more of a statement than a question, but we'll get your thoughts on it. No mention that elbows add significant flexibility and piping can be configured to allow torsion, which is more flexible than pure bending.
Yeah, so that's right. It's just because of the time of the webinar. So yes, as you have your different elbows, how you position them, if you allow the pipe not just to bend but to twist in 2 dimensions, that will add to flexibility. But again, if you're trying to do that type of thing, you almost certainly will have to use formal pipe stress analysis because doing that by hand would be very complicated and probably not worth your time.
Okie doke. Time for one more, if that's all right. So last one we'll have is, how can you assess stresses due to thermal expansion by hand calculation methods?
Yeah, so again, we briefly covered it. If you have very simply defined system where you can use one of those monograms that you can find in textbooks like Kellogg's and similar, then you can follow them using hand calc. But if you have something like this piping here, near impossible. Again, back in the day, people will use all sorts of different rules of thumbs and monograms and approximations, but it would not really compare with what you can get out of a pipe stress analysis in terms of accuracy and less conservatism.
Excellent, thank you. Alex, we've probably got another hour's worth of questions, unfortunately, but we'll have to call it a day. So unfortunately, we've had to disappoint a few people with their questions. But as I mentioned earlier, the website is a huge wealth of information. If you want to find anything out in addition, certainly would recommend looking at some of the courses that you're running over the next few months as well. Just want to say probably a virtual round of applause is probably occurring, Alex, for the presentation. So thank you for your time today. And hopefully it's been very useful for everyone who's attended as well. And thanks for supporting the webinar, and hope to see you all soon.
Yeah, well, thanks a lot to everyone who attended, and thanks Robert and Darren for running it and helping organize. I thought it was very good. A lot of great questions there. I'm sorry we couldn't get to them all. But yeah, as I say, so we do run courses on nutritional pipe stress analysis. It's a 2-day course, whether it's virtual or whether it's face-to-face, it's the same amount of content, and we can go into a lot of those queries and discuss them and cover more details. Hopefully that kind of perk people's interest in pipe stress analysis and whether they need to do it or not, depending on the type of projects they work on. So thanks a lot.
Yep, excellent. And the slides and the presentation will be available on things like our YouTube channel as well. So if you've not had a chance to capture all information, hopefully you can find more details there as well. But thanks again, Alex, and no doubt we will speak to you soon.
Thank you. Perfect.